Good morning, good afternoon, and good evening, everyone. I'm Rob Mueller, and today I'd like to talk with you about Intel's software libraries for cryptography and how to achieve compliance with Federal Information Processing Standards, FIPS, ensuring security and privacy for stakeholders as well as customers. We'll cover the basics of the FIPS standard and compliance, talk about the Intel Cryptography Primitives Library. We'll showcase a demo on how to test for and achieve FIPS compliance for a program using AES-GCM encryption. And lastly, give you pointers to resources to take advantage of everything we'll talk about. But first, let us talk about security and privacy, and let us talk about what FIPS really is all about. So let's start with the purpose of cryptography. Encryption really is important anytime we handle personal data, medical data, sensitive data, security critical data, mission critical data, and financial data. So in short, encryption is important whenever we handle data. It applies to data at rest and data in motion. FIPS 140 and globally speaking ISO 19790 define encryption design and testing requirements. Although only mandatory for organizations directly interacting with governments, many industries like healthcare, finance, or law enforcement regularly rely on these frameworks to ensure privacy and security for all types of data handling. That said, the real-world industry adoption has expanded and now reaches into applications like cloud service providers, security and authentication, communications, conferencing, manufacturing, tamper-proofing, energy and utility companies, autonomous and unmanned vehicles. FIPS, thus, is the de facto programming standard and regulatory backbone in the modern world where decentralized data storage is ubiquitous. Some more details and links for further study, and some more detail and background on FIPS itself. FIPS was jointly developed by the United States NIST and the Canadian Communications Security Establishment, CSE. FIPS 140-2 defines the minimum security requirements for cryptographic modules in information technology products. FIPS 140-3 now additionally provides alignment with ISO 19790 standard from 2012 and regulates vendor evidence and establishes testing and validation authority. So we basically now have a process for certification and approval. FIPS 140-3 defines 4 security levels, from level 1, the easiest, to level 4, the most stringent. Software may be certified up to level 2, and the categories covered are, well, plentiful. So if you look at software, we're primarily talking about things like roles, services, authentication processes, finite state model confirmation, cryptographic key management, and self-tests. But the standard itself goes beyond that. So we're also then talking about specifications, ports and interfaces, physical security, operational environment, electromagnetic interference, electromagnetic compatibility, design assurance, and attack mitigation. The NIST Information Technology Laboratory operates a program that validates the FIPS-approved cryptographic algorithms in a module. There's the Cryptographic Module Validation Program, CVMP, for application, module, and product certification. And there's the Cryptographic Algorithm Validation Program that ensures compliance of the ingredients that are being used and of the algorithms that are being used. We need FIPS-compliant algorithms and libraries to create cryptography modules, programs, implementations that can be certified. NIST's Cryptography Algorithm Validation Program, CAVP, provides that framework to ensure compliance. It covers which specific algorithms can be approved for compliance, and CAVP FIPS compliance registration of used components or libraries from vendors like Intel gives you the peace of mind that your project can indeed in the end be certified using NIST's CAVP program. So, the Intel Cryptography Primitives Library. The next generation of the Intel Integrated Performance Primitives Cryptography will be a spin-off from the Intel Integrated Performance Primitives and will become its own product, the Intel Cryptography Primitives Library. FIPS compliance is only one aspect of this powerful collection of this open source cryptography routines covering methods and algorithms used in telecommunications, banking, data security, ID authentication, privacy, secure autonomous AI and cloud or database security. It provides solutions for all aspects of life and work. It is even ready for the rapidly evolving world of post-quantum encryption with support for XMSS, Extended Merkle Signature Scheme, and LMS, the Latent Michaeli Signature Hash-Based Signature Cryptography Scheme. The goal of the Intel Cryptography Primitives Library is to improve the performance of cryptographic operations in multimedia, enterprise data, embedded communications, and science, while providing a common cross-platform, cross-operating system API for cryptographic operations. Its key tenets are to help you with security, achieving small footprint size, to be optimized for Intel hardware cryptography instructions and extensions, to ensure kernel mode compatibility, to have an inherently threat-safe design, to enable and ensure data protection for the post-quantum era, and to provide everything you need for FIPS 140 compliance. So on this slide, you can see a representative list of all the types of cryptography algorithm support it provides for authentication, OpenSSL, prime number generators, public key encryption, symmetric cryptography, and data authentication for post-quantum cryptography. So, back to FIPS. As mentioned previously, we have 140-3 algorithm FIPS compliance certificates on file, and you can see them up here on the slide. The multi-buffer encryption routines and regular Intel Cryptography Primitives Library have module identifiers and FIPS-approved service query routines to clearly identify the algorithms you are using for documentation and CAVP certification purposes. The self-tests provide the key building blocks to ensure compliance for your application, leveraging our library as you are developing. Building an application using Intel cryptography in FIPS mode with compliance testing is quite straightforward. You use to define -d IPP-CP_FIPS_mode equals on as a CMake build flag to enable APIs for self-tests and FIPS support queries. Here you see examples on what this looks like inside your makefile. So you basically just call the Intel OneAPI DPC++ C++ compiler with the appropriate define, or similarly, you do the same if you're using GNU's GCC compiler. For FIPS 140-3 Level 1 requirement self-testing, we provide the following APIs. As you can see, a few have to be covered by the user application as they really test application design specific requirements. For the majority, however, we do indeed have APIs and we can help you achieve compliance and certification through that. More specifically, looking at the cryptography execution flow, the FIPS self-test flow is as follows. The library uses special structures, specifications, and states to store context information and provide service functions. It provides a cryptographic algorithm API, both FIPS compliant and non-FIPS compliant. FIPS self-tests API and service routines can then be called to query if an algorithm is FIPS compliant. And this covers, from the previous slide, APIs for requirements 2, 5, and 6, for instance, to achieve level 1 specific requirement. It also stores and manages version information, is the API for number 1 in the requirements list previously mentioned, and it provides a dispatcher control. Lastly, the dispatcher then decides on the optimal code path depending on hardware features and application settings. The FIPS-compliant self-test for a given program and/or algorithm follows a simple step-by-step flow as well. First, we identify whether the use of a given algorithm is approved to be used for FIPS compliance or whether NIST decided it is not in line with some of the key requirements for FIPS compliance as outlined in the standard. Then we identify the memory buffer size that needs to be allocated to provide the extra space for compliance testing. Lastly, we'll call the self-test routine for an algorithm and return compliance status before calling the cryptography function itself. All right, so let us actually demonstrate FIPS-compliant encryption use on the example of AES-GCM, Advanced Encryption for Communication and Authentication. AES-GCM, Advanced Encryption Standard Galois Counter Mode, is a commonly used encryption standard for secure data exchange in finance, communications, and edge-to-cloud security. It provides authentication and encryption for confidential data, thus not only protecting the data, but also ensuring its integrity across the encryption, transmission, decryption pipeline. It is covered by NIST Special Publication 800-38D as one of the recommended cipher blocks and thus also approved for FIPS compliance in its basic algorithm design. Of course, our Cryptography Primitives Library is able to take advantage of a whole variety of Intel architecture encryption and vectorization instruction extensions. So here we go. Let's see how it's done. Let us demonstrate the use and enforcement or testing of FIPS compliance in the context of the widely used AES-GCM encryption. As a simple example, we apply GCM to a regular text string. First, we initialize and allocate memory for the data that is about to be encrypted. The variable ptext contains the plain text, and the output of the GCM encrypt function is the resulting ciphertext. To introduce FIPS compliance to this example, we will want to add a FIPS testing and enforcement section. Within the markers of this section, we first check if the algorithm is approved for use with FIPS, whether it has been tested by NIST and found compliant with the standard's tenets. At the same time, we also check whether this function is already covered by the Cryptography Primitives Library. Failure of this test will return -1. The next step executes a functional self-test. As part of that, we allocate a memory buffer and check for parameter size and type. Lastly, we call the function with a self-test wrapper instrumentation. Failure of these tests will again result in -1. That is all there's to it. The original GCM encryption code remains completely unchanged, eliminating the risk of any functional or security impact of the test itself. Finally, let's download the Intel Cryptography Primitives Library GitHub repository by typing git clone with the repository's URL. Then we set up the environment. The build.md README document in the GitHub repository provides all the details on which build tools are expected to be present on your build system. Now we are ready to configure our project using CMake. CMake -b build directory defines for Intel 64 architecture, FIPS mode enabled, and the library installation directory. And now we can use make to build the FIPS-enabled library using multi-threaded build mode and then install the build result. Finally, let's compile the example fips_sample.c against the static library which we just created. Running the sample, we can see that the application is finished successfully and indeed FIPS 140-3 compliant. The Intel Cryptography Primitives Library makes it easy to add data security to your application and use case, protecting your customers' data security and privacy for sensitive data. Not just that, with FIPS compliance self-testing, nothing prevents you from achieving the same level of protection and peace of mind as government contractors and agency, potentially opening those markets up for your production as well. So My call to action: protect your customers and stakeholders. We all transmit and store sensitive and mission-critical data. Most private and business data these days lives in databases or in the cloud. Protect critical infrastructure in banking, energy, utilities, hospitals, public safety against malcontents and black hat attacks. Encrypt data in flight between data center and local devices. Encrypt and protect non-public personal information, NPI, as well as sensitive but unclassified information, SBUs. Use a common cybersecurity standard as you do so, FIPS 140-3. Find out more and follow the 2 links to the Cryptography Primitives Library FIPS documentation on GitHub, and also have a look at the FIPS 140-3 standards details on the NIST website itself. Thank you, and please don't hesitate to reach out to us with any questions or comments you may have. Thank you. Talk to you next time. Goodbye.